Okay, so I'm going to talk about wide-field slitless spectroscopy with NIRISS. This is my outline. So first of all, I'm going to talk a little bit about what's been done with Hubble recently, and Ichi touched on that a little bit. I'll go into a bit more detail about the type of science that's been done using the Hubble grisms. Then I'm going to tell you what we have inside the NIRISS instrument for using this mode of spectroscopy. Then a bit about the observing sequence, how you'd actually go about carrying out this kind of observation. Then something about the data analysis that we need to be able to do to recover the spectra of the sources. And then a bit about the performance, how you can do in terms of the sensitivity and the issues you might have with contaminating spectra that overlap each other on the detector. And then a little bit about a comparison between using the MOS on NIRSpec and using NIRISS, along the lines that Ichi was just talking about. So here's a little montage of some of the things that have been done with Hubble recently. There's been a big explosion, I think, in the last few years of slitless spectroscopy on Hubble, which has given us our first look at doing near-infrared spectroscopy in space. And particularly for high redshift galaxy work, there's been a lot of great things that have come out of it. So here in the top left, we have, this is the GRISM spectrum, redshift 1.9 galaxy with HST with wide-field camera 3 grisms. And so this is a passive galaxy, evolved elliptical type galaxy with an age of 1 to 2 gig years. And you can see the kind of continuum spectroscopy you can get. So this is fairly low resolution. And the resolution you can get with NIRISS is going to be very similar to what we see with the WIF-C3 grisms on HST. So it is low resolution. You don't get the same high spectral resolution that you may be able to get for identifying individual absorption features. But you can see that the broad absorption features you see in these evolved galaxies are well recovered by the data. And in comparison here are some ground-based data from X-Shooter on similar brightness targets, which do not reach the same sensitivity that you can reach in space. So although generally people think about the wide-field slitless mode using a grism at low resolution as being all about emission lines, I want to iterate in this point that it's also continuum spectroscopy can be very useful as well. So moving on to the emission lines, here's an example here from the GLASS project, which is using frontier fields and other lensing clusters to look at strongly lensed galaxies in the background. So these are low luminosity dwarf galaxies at redshifts 1 to 2. And in this paper from Tucker Jones, there's spatially resolved emission lines of these arcs. And so from the imaging, this is the stellar mass density. So you have an idea, a map of where the stars are in the galaxy. And here you get a map of the metallicity from combining emission line ratios. So you can actually get resolved metallicities at very high resolution, sub-100 parsec resolution in distant galaxies. Here's an example from the 3D HST survey. So they carried out a survey of the CANDLES fields, going for lots and lots of galaxies to build up a big sample of galaxies. You see redshifts up to around 3. And this is a montage of all the spectra thrown together. So there's 40,000 spectra here of different galaxies. So great thing about this mode is you get lots of multiplex, lots of galaxies at once. And you can see in this montage the strong emission lines passing through H alpha, N2, silicon, sulfur 2 here. And then we have the O3 and H beta and oxygen 2 as well. And then down here, also from the 3D HST survey, this shows you a plot of the density of galaxies in the field. And the upper panel here is just using photometric redshifts based on broadband information. And you can see how there's evidence for these overdensities. But if you now use GRISM redshifts, because of the emission lines, you're getting much tighter constraints on the redshift. So GRISM redshifts are accurate to about 0.003 times 1 plus z. And what that means is you can really identify the high density regions in physical terms much better than you can when you're just using photometric redshifts. So that allows you to do all kinds of things of relating the galaxy properties with their environment. So Alex showed this earlier. This is the 2 wheels that are in the NIRISS instrument. As he said, NIRISS has 4 observing modes, and the way in which you pick which observing mode you want is just by spinning these wheels until you get the right alignment of elements. So in the pupil wheel here, we have 6 filters. So these are all the short wavelength filters below 2.5 microns, which are used with the slitless spectroscopy mode. So you pick one of those filters, and you combine it with a GRISM, and there are two GRISMs here, GR150C and GR150R. And those are the low-resolution wide-field slit spectroscopy GRISMs, and the C and the R correspond to whether you're dispersing the spectra along the columns or the rows. As you'll see in a second, there's the two orthogonal GRISMs to mitigate the contamination. And the field of view, as we've heard several times today, is the same as the imaging field of view, so 2.2 by 2.2 arc minutes. And this is what the spectra actually look like. So this is some calibration data we got during the CV3. And this is actually a co-edition of several images together, where you see the direct image position of the test source is here. And for the GR150C, the spectrum is, for the GR150R, it's along the rows. So this is the 0th order, this is the 1st order spectrum, and there's the -1 spectrum. And then for the other GRISM, it's dispersing along this direction, and so your spectrum is there. And so you can see that by matching up, if you identify a source in the two orientations, you can actually interpolate its original position and therefore determine the wavelength. So what do you get in this mode? You get spectra of all the objects in the field, obviously, and that can be a lot of objects. So if you remember the image of a simulated deep field that Jerry Criss showed earlier with his very high redshift galaxy that was just a tiny little blob, you saw how many galaxies there were. Well, you get a spectrum of everything in the field with this mode. And to put that in context, there's about 3,000 galaxies in a typical field if you're going down to magnitude 28. So you can get a very high multiplex factor. The spectral coverage you can get is almost complete if you use 4 of the 6 filters between 0.9 and 2.2 microns. And that means over this observed wavelength range, you can get at least one strong emission line from redshift 0.5 up to redshift 5, and it covers Lyman alpha between redshift 6 and redshift 17. As I mentioned before, because the spectral lines are basically unresolved at this resolution, you get a map of the emission lines. So if you want to look at maps of different emission lines, it's a very powerful mode. So as Ichi mentioned, similar to an IFU, with an IFU you usually have high enough spectral resolution that you're actually able to get information along the velocity. Here you don't have that velocity information, but you have lots of simultaneous maps of emission lines in the field. I mentioned already the cross-dispersed GRISMs. It's a simple observing mode, so there's no target acquisition required. You just go straight to your field and start observing. And again, for parallels, this would be very useful mode. The resolving power ranges between 100 and 200, and the spatial resolution, each pixel is 60 milliarc seconds, so that corresponds to around half kiloparsec for high redshift galaxies. So what's the observing sequence like? Basically, you take a direct image so that you know where the position of the galaxies are or stars in your field, and then you put the GRISM in, and that disperses the light. And then you're able to match up the amount of flux coming through in the image of each object, and then to the spectrum that you get from that. And it's very important for being able to properly interpret your field that you have the image that's matched with the GRISM exposure as well. Now, the filter wheels, they don't always come back to exactly the same position, so there will be some rotation if you spin the wheels while you're observing. So we recommend that if you're going to be wanting to co-add the data, then that you don't do any turns of the wheels in between. You do all your dithers first. Of course, it's also best from the mechanism usage point of view. So this is a picture of the APT template for the NIRISS mode. So here you define your target information and which kind of template, which instrument you want. Then down here, you have the NIRISS wide-field slit spectroscopy tab. And so the first thing you have to do is define what dithers you want. So we have a 4-point dither with set offset ranges that are particularly good, giving you subpixel sampling I'll talk about in a minute. You have to define your filter and your GRISM, and then the details of the detector. And then at the moment, the way that the APT template is laid out, this is for the spectral part of your observations. There's also the direct image, and you lay out the direct image part of your observations as well. And so right now, the way this template works is that for each of these 4-point dithers with spectroscopy, you'll also take a direct image at the beginning and at the end of that sequence. There is actually work to make this more flexible hopefully in a future version of the APT, which will be particularly important when we're working in parallel mode. So these are the dithers. So as mentioned already on the imaging talks this morning, getting subpixel sampling is particularly important, and especially for NIRISS, because here we're working in the short wavelength end with NIRISS, so we are very much undersampled. So the typical 4-point dither pattern uses half-pixel subsampling. So we have 4 dither points here, and they have half-pixel offsets between them, as well as the multiple pixel as well to move over detector defects and move on to different columns and different rows. And so this is what it looks like if you look at the sky and you take your point source and you dither it around in different places, and then the recombination. These are just 2 different stretches for the same information. And you can see you've got a nice tight core now in the drizzled image. If you're working in parallel mode, then you'll be able to select either that you want the dithers, which are optimum for the other instrument, or the dithers that are best for this mode, or some kind of compromise between the two, the dithers that work best for the 2 instrument modes in parallel. So for the data analysis, obviously we have a data pipeline, which we're going to hear more about tomorrow, and that's going to do a lot of the data reduction for JWST data. And certainly, we're working hard to get as much as possible in terms of the kind of data reduction you need to do for this mode into the pipeline, so that it'll be there and the same steps will be able to be carried out for all the users. But it is a complex mode, and it's likely that when you get towards the latter stages of interpreting your data, you're going to want to take it outside the pipeline and use other tools to do the analysis. But certainly for quick look and for simple cases, what you can get out of the pipeline will certainly give you an answer for what's the spectrum of a particular object you're interested in looking at. As you can see here, so this is a simulation. So this is the F200W filter. And so this is just the direct image. And this is one of the frontier fields lensing clusters. So you can see here we have, so this is at a very high stretch level. And so these are the bright cluster galaxies. And there's a few of them here. And in between them, there's also intra-cluster light of stars that have been stripped out of the galaxies. And so there's a lot of stuff around here, lots of other cluster galaxies, and obviously we're interested also in the very high redshift lensed galaxies behind, which you can't really see in this picture, but they're all in these regions around here. So once you put the GRISM into the field with NIRISS, this is the kind of data you get. And now what you're getting is you're not just getting a first-order spectrum for everything, which is what you see mostly along here for the bright galaxies. There's also a second-order spectrum that comes further over this way, and there's the 0th order as well, which comes in here. So it gets a bit more complex, and you get a lot of overlap between things. So you can see that if you're interested in sources around here, you're going to have to do quite a lot of work to recover the spectrum because there'll be overlap between different sources. So this is now zoom in onto just 1% of that field of view that I was showing there. So 1% of a NIRISS field. And this is the direct image here, so this is not right in the cluster core, this is off to a region away from the core. So these are mostly now very faint distant galaxies, and these are the spectra. And so you can see even in these regions there is still some overlap, and you need to do some work with contamination to be able to interpret the spectral features of one source compared to another. But what you can see here is that there are a lot of emission lines. So lots of these sources, here's a lensed source here, and then over here you can see there's the continuum for this source, but then there's also a strong emission line here. And in fact, most of these little blobs you can see here are emission lines. So one of the discoveries that's been found with the Hubble GRISM data is that as you go to high redshift, sources tend to get much stronger emission lines. And so an instrument such as NIRISS, and also with the NIRCan GRISMs, you're going to be able to detect a lot of these high redshift, very high equivalent width emission line sources. So for data analysis, so one of the things, and Ichi has mentioned this already, Gabe Brammer's working on this new data analysis software called Grizzly. And here's an example of what you can do with Grizzly. So this is using HST data. So here's 3 different imaging filters and a color image of these galaxies. So if you look at this one here, then the spectrum, the simulated NIRISS spectrum of it looks like this. and this includes all the contamination from other things in the field. And then if you model the contamination of the other sources, such as this one here, so a much brighter source, you can see here that's contaminating this part of the spectrum, but you can do a full model, okay? You can do a full model of what that source spectrum looks like, and you can then subtract it out. And once you subtract it out, you're left with this, which just has the spectrum of the source that you're interested in. Now, you can see here for this source, we have, you can see that there's continuum, and then there's also clearly an emission line over in this region. So by modeling the continuum and the emission line separately, you can then subtract off the continuum of the galaxy, and then all that you're left behind with is this map of the emission lines. Similarly, this source over here as well, where you can also end up just with the map of the emission line. And then if you imagine if you have several different emission lines in the range, might come in different filters, you can get maps of the emission line ratios. For the sensitivity, this shows the sensitivity curve in terms of the line flux sensitivity using the 6 different filters with NIRISS. So you can see the sensitivity is it's a bit higher down at the very short wavelength end, and then here you're looking at around about 7 times 10 to the minus 18 with the F150W filter. And in terms of continuum sensitivity, then you're getting down to magnitude around about 25 in 10 to the 4 seconds. Here's another simulation. This is for the very high redshift 11 galaxy. So the galaxy with the highest spectroscopic redshift at the moment that's known comes from the Hubble GRISM data. And the Hubble GRISM data is basically the black line here, heavily binned into these very wide bins. And that's what the current spectrum looks like. And this is a NIRISS example simulation for the same galaxy at 3 hours per filter. And the NIRISS data now is these the thick colored curves here. So you can see a much better idea of exactly where the redshift of the break is. So this illustration, and you can see the break here as well in very sharp in the 2D spectrum. It's just an illustration that these GRISMs are not just for emission lines, but also continuum breaks. And particularly for Lyman alpha at high redshift, where the light for Lyman alpha may be disappearing because of absorption in the intergalactic medium, continuum breaks will be a very important way of getting redshifts. So my final slide is just to sum up that this mode has unique capabilities, a very high multiplex factor. If you want to get spectra for loads of sources at once, this is the way to go. And if you want maps of the emission lines for a large number of sources in the field, this is the only way of doing it in this wavelength range. And another thing is there's no slit losses, so it gives you very accurate fluxes for the emission lines as well. And finally, here's another simulation. So this is a redshift 2.1 galaxy. And at this redshift, you get different emission lines turning up in each of these 3 filters. So you can see we have an emission line map for H alpha, O3, and for O2. Thanks.